Hello, Kudus. Kudus.
Ma'am,
Kudus. Please send me
yes,
that
ma'am.
link urgently. Send me the link. He can't get on board.
Okay,
No,
okay.
no, no. Please send me the link. Okay. You're very much welcome, everybody. Thank you so much for joining the session. It's our very special session here to make significance. It's my pleasure to welcome a speaker, a very special speaker to this session. I'll be talking about him a little later, but it's a motivational talk. So you would listen. If you have questions, send questions, but it's not going to take questions. This session is actually a, a time that we reflect together. Like I often share, and for which many of you do listen and hear, is that Africa is way behind in terms of a research output. Our research output is one of the many ways we can tell our stories, but oftentimes not other people tell our stories, even in our research endeavors. I share a powerful story, a powerful slide many times when I present this kind of talk, where we do know that HIV, TB, and malaria is a problem of Africa, possibly Asia. But where do you find the, the research products about HIV, TB, and malaria? It's the global north. So they are telling our stories. And that's where the phrase from Shaya Bimbola becomes very powerful. There's something called the foreign gaze. When somebody tells your story, they tell it from the way of their own understanding. And therefore, many times they will malign you because the way of your stories is not the way of their own cultures. And therefore, their perspective and the lens with which they read and tell your story is against their own decimals. There is an Igbo proverb that says, until the day the lions can tell its stories, the hunter will remain the victim. No lion is ever able to tell the story that I killed the hunter. The hunter will forever tell the story, and therefore they become the majority of the decimals of killers of lions. We need to embrace the power, not only to tell our stories powerfully in platforms where it matters, but also to be able to tell it with pride the way it should be told. Today, we're bringing onto this platform one of the best there is around the world, who not only tells a story powerfully about Africa, but dares to get into the den or the places where otherwise you would say is exclusive, the rights of Nobel Prize winners or thinkers, people who think outside the box. Not just think outside the box, but they are the ones that dare to think about traveling to the moon. It is indeed a pleasure to welcome Ife to share with us the power to dare to dream. Please welcome with me Ife Dayo. That's how I call him. He would introduce himself, tell us about yourself, and let's listen to his story and be inspired to not only do as much as he's doing, but even far more. Whatever your little dream, make it big. And that is what we're sharing today. Over to you, Ife Dayo. Yeah. And please welcome Ife Dayo with your emojis, your words, just share as emojis as Ife Dayo brings up and can share slide. Over to
First of all, I'd like to thank Professor Moringa for the um, introduction. I'll try to live up to her expectations. Um, I also would like to give her flowers because I think that she's not only a remarkable thinker, but someone that I am also learning from as I sort of start to sort of make these connections within the Nigerian and African ecosystem. Furthermore, I am humbled that I've been invited to speak and sort of explore some very important and nuanced things as it relates to research, science, creative thinking, storytelling, and so forth. I've prepared a slide for you all to sort of capture um, some of these things. So I'll share my screen. If at any time someone has a question, please do interject. As much as this is a talk, I want this to be a conversation. And if certain things are not as clear, do try to point that out. What I guess I have to be allowed to share right now. Okay, so I think that is on now. So please let me know if you can't or can see my screen. Um,
The screen is coming up and we can see it now, but it needs to be in full screen.
Excellent. Okay, so I'll just minimize this a bit. Um,
Yes, we're there.
excellent, excellent, excellent. So the title of this sort of talk, as you can see, is the art of storytelling and persuasion. Um, you know, um, my first degree was in philosophy of history. Then I moved into cosmology. Then I explored a little bit of neuroscience, and then my PhD was in theoretical physics. And one of the things that I am trying to do is basically solve the brain using physics and mathematics. And that leads me to my next slide. And I just want to give a brief background on sort of the space that I operate in. I'm a neurophysicist, and what that means is that I use physics um, to understand the principles or the laws that govern biological functions, such as thinking, moving, seeing, and so forth. It'll become a little bit more clear why these two fields are important and why these two dots are, I think, will unlock our understanding of both the brain and our place in the universe, right? Um, and so I want to focus on seeing. Um, so what I'm going to do is I'm going to sort of use this laser pointer as a way to sort of orient you into the visual fields that I want to highlight. So what I'm showing here is a human eye, right? This notion of seeing. So I'm just going to highlight this one biological function that I'm going to dive into in this talk. And you can see that this is a biological behavior that you and I perform most of the time, right? We move our eyes. These are known as saccadic eye movements. And this number here is the degrees of visual angle that you and I are able to see. And so if someone was to, let's say, put their hands up behind my head, I won't be able to see it, right? Because my field of view is limited at 210 degrees. If you look at another biological species, right? This is a mice or a rodent, right? And you can see that its visual field is a little bit wider, but it also makes these eye movements. And then if you kind of go back furthermore, you'll see that this animal, which is a fly, a fruit fly, mosquito, right? They have almost panoramic 360 view. And what I've put here is obviously some of you will know, right? This is a citation, sort of highlighting that I got this image right from someone else's study. And so I think I'm going to point out these small things throughout the talk as a best practice when you sort of speak about your work. The reason why I didn't put the citation on these other two is because these are things that come from my lab, and so this is an original contribution that I'm making to the slides. Again, excuse me if some of these things are redundant to some of you, but I think it's important for us to be very precise when we speak about, storytelling and also assigning credit to the people that actually contributed to our stories. And so why I'm showing you this just to sort of articulate the idea that I'm a neurophysicist. I use physics and mathematics to understand biological systems. And the system that I'm going to talk to you about today, and I'm going to use a lot of examples, um, is the behavior that I'm going to talk about is the behavior of vision. And the system that I'm going to use a lot is the rodent. And some of it may or may not be apparent while why I'm using that, but I'll try to make that a little bit more transparent. So in order to study these systems, experimentalists, right, they have these setups. And these setups we use to understand one of the units of the brain, right? So in physics, for example, we try to study particles, which are the units and matter, right, which are the units of the universe. But when you are trying to understand another system, right, another dynamical system, dynamics in this sense means something that evolves through time. The unit of this system, right, is a neuron, a cell, right? And so what you see here is I'm going to play this, and what you're going to see is you're going to see the thing that this animal is looking at, right? You're going to see its eye movements, right? The eyes moving, right? And then here is the actual neural activity. So there's actually a material that is, moved into the brain that is actually recording this animal's neural activity, right? When the electrical signals are occurring as it's moving into the world. And you might wonder, right? Like, why would you even study such a system? Well, unfortunately, we can't do the same thing we would do to a human being, right? And so there's an assumption here that um, these systems are genetically analogous to humans, and they also have the same type of cells that most human beings would have, right? And so this is kind of one of the reasons why you would want to explore such a system, right? And so what I'm going to now show you all will be one of the first people in the world to ever see this. Um, and I want you to, I'm going to show you something that was developed at this institute is called the Allen Institute. It's called the Allen Institute is because it was founded by Paul Allen, the co-founder of Microsoft. And at the Allen Institute, what they have done is $100 million project where they actually they actually look inside of the brain. And so this is the first human connectome ever made. And what you're going to see is you're going to see kind of almost like this universe of the cells in your brain. And so what's being shown here are synapses, right? These synapses are basically how cells talk to each other. And I'm showing you this because this is a summation of a lot of people's stories, right? How they've told the stories, the things that they're talking about, and so forth. And so in the paper that preceded, there was a paper that appeared before I showed these slides. And you know, one, I just want to give you an opportunity to sort of appreciate the science that is being done at this institute, but also this is kind of the things that physicists and theorists like myself use that we're trying to sort of understand, right? I'm gonna let it play just a little bit more so you can just appreciate um the material that is needed. So, for example, this is another group and the stories that they told published in Nature where they wanted to understand different aspects of this data. Um, and so when I'm speaking about the dynamics or the story, the elements of the story that I'm trying to tell, I'm referring both to the behavior of eyes movements and so forth, and also these individual neurons and their neural activity and so forth. So here's a case of, certain cells as the animal is moving, these cells are the ones that are activated to enable you to be able to, let's say, walk from point A to point B. This is all part of storytelling, right? Being able to help people visualize what you want to say, being able to sort of make these connections. Um, and again, like I said, this is kind of some of the first publicly available articulation of this data. And I wanted to share that with you all because I think Africans like myself and you all in here, we deserve to sort of see these things and also tell stories about these things at this level as well. Yeah. So now I'll move on to the more practical aspect of this talk, which is kind of the part that will be a little bit less, um, a little bit more, hopefully accessible. So the first thing that I'm not exactly sure why this red part is here, but we'll continue. Um, so let's get right into the bread and butter of the talk. Um, this I'm going to start with this idea of advocacy mindset. And the question here is, why you must be your own advocate, especially as an African scholar. And I'm going to tell a story and give you an example of why your advocacy is important for your own work. But I'm going to start, however, with this simple example. Here's Isaac Newton, right? For those of you who may know some of his work, he's probably one of the most influential scientists and storytellers of human history. What I'm showing here is a ball on top of an abstracted line. According to Newton's story, if you push this ball, right, the ball will move because you've applied force. And so we get this famous equation F equals ma, the mass and acceleration, right? And so that was the story that he told. And this is referred to as classical mechanics. But I want you to engage in a thought experiment with me very briefly, maybe 30 seconds. When you look at the sun, no one's actually pushing the sun, right? There's no invisible hand pushing but the sun appears to move most of the time, right? So someone else came along and said, "Hey, Newton, your story is not quite accurate. There's something else that's happening when we think about the universe." And so for him, this is Albert Einstein. And he said, "No, what's actually happened is that the fabric of the universe, which I've abstracted here, is actually curved. So you can imagine if I put a ball at the top, at the end of a mattress that's curved, that you don't need to apply any force on that ball. The ball will just naturally move." And this very simple but powerful abstraction redefined our understanding of the universe. In this case, within the field of physics, where Einstein made the point and said, no, space is actually curved. And we think of this as what we call curved space-time. And till this day, Einstein's story, right, is still how we understand the nature of the universe. Notice that the difference between Einstein and Newton was a very simple story, but they used the same exact objects, right? And so I wanted to use this example not only to articulate the idea of both of these individuals articulating their story, but also the importance of them advocating their own story through simple storytelling, simple abstractions. Here is kind of where I come into this picture because I'm highly influenced by these people. Number one, I'm not a white man. And that's why I said that it's important as Africans for us to be in these spaces and start advocating our own stories in very rigorous but important ways. This field that I've invented is called retinotopic mechanics. It's a summation of both physics and biological systems. And so let me kind of explain to you how I advocated for my theory. Although, as you know, right, it's very political in the field of science or just, life in general. And so a lot of these people and a lot of my work still has to fight the racial boundaries of things. But nonetheless, these are the spaces that I think we should start to explore. And these are spaces not just in physics, but in whatever field you are, history, life science, dare to jump into the ring, if you may. Of course, the rigor has to be there, but you as an African, we have untapped mental capacity to begin to write our own stories about the nature of the world, the nature of the universe, the nature of economy, the nature of medicine, and so forth. And so I'm going to explain to you in this work what I've done. What you're seeing here on the right hand side, this is the phenomenon that I use to describe retinotopic mechanics. If you were to move your eye from here to here, what you actually experience is this kind of blur, this motion blur. But you and I don't experience this motion blur in our day-to-day lives. For example, if I moved my eye from here to here, I don't experience this blurriness, right? But imagine you were to take a camera, right, that had the same optics as you and I, right? A camera, the lens, right? We have lenses, right? Imagine you took a picture of a fast moving object. If you looked at the picture that you took, you would see that motion blur. But somehow the brain has evolved throughout its entire evolution to cancel out this motion blur. So you and I can see this continuous, smooth perception of the world. But no one actually knows how that is occurring. So I found this as an opportunity to bring about the mathematics that I've invented to explain something that they couldn't explain. When I say they, I mean the Western discourse. And I won't bore you too much with the actual mathematics and the nuance of the storytelling, but what I introduced into the field is the idea of thinking of cells in the brain as springs or spring-loaded sensors. And in physics, we think of springs as like, excuse the jargon, but harmonic oscillators, like oscillatory systems. And so what I've done is sort of reimagine how cells should be understood when we think about these types of movement phenomenons. And so what you see here is just a simple example of a cell undergoing these different type of forces. And these forces are all kind of ways to explain how your eye is moving in the world and how you're able to sort of experience this kind of smooth, continuous perception of the world. The details here aren't important. What's important here is to just get a sense of the importance of or the possibility of you being able to look at a problem, create your own mental experiment, your own mental abstraction, and then execute that in a way that is understandable and something in which is publishable at the highest level. I ended up publishing this work. I don't like to publish that much. And when I do publish, I like it to be foundational. But I ended up publishing his work in Physics Review as a single author, and Physics Review is probably one of the top journals in physics, in which Nobel Prize winners are always, competing for publication in that journal. And so this is kind of what, if you were to simulate my field, this is kind of what you see when you this is kind of what this theory says when you're in the world moving around. This is kind of what the retina, what the visual areas in your brain are is doing as you're moving into the world. And you know, on where I have this mouse here, right? Notice that this thing is not as dynamic. It's not moving as much as this one. This is a simulation of, let's say, you saw a dog or someone pointed a gun at you, right? Your field kind of collapses. You focus right away at the thing that scares you the most. So you have this thing called tunnel vision. And so my theory explains this biological phenomenon where even if something was at the right of you, you wouldn't even be able to actually dynamically move in that space because you're locked in into that state of fear. And this is what happens when you have things like norepinephrine, when you have your adrenaline system running, when you're hungry, so forth. So it explains a lot of biological states. Here is, let's say, someone with hyper attention deficit disorder, right? Where no matter what is presented in your visual area, you give everything equal attention. So you attend to that, you attend to that. You can't actually focus on one thing or dynamically move, as is the case on the left hand side. Again, don't worry so much the um about the details of the science, but more so what I've tried to take you through is, how to start from first principle, come up with your own story, work out the nuances of that story, find ways to visualize that story so people can at least understand a little bit more of what you're doing, and so on. And that's kind of what I've tried to do with this simple example of the one of the foundational papers that I published called retinal topic mechanics. And so I'm going to continue now, and I'm going to move on to a second point, setting the stage. And I use the word setting the stage because life is a theater, right? Sometimes you have more buffoonic and more idiotic stages like Donald Trump and the American political system, right? That is a comedy, right? Of course, the influences of that stage has significant effects on people's lives. But really, when you really get down to the art of storytelling, the art of persuasion, it's like a movie, it's a theater, it's a stage. And so the first thing I think as authors of a stage is you have to set the stage. So remember, right, that when I first was kind of given this talk, I set the stage with Newton and Einstein. And some people may be like, and I've experienced this before when I give talks and when I, you know, talk to my white colleagues. Some of them are like, how dare you think that you can compare yourself to Newton and Einstein, right? But for me, not only am I fearless, the lineage and the community that I come from has given me the sense of audacity and the sense of courage that this is a stage that I belong on, right? And so when you're thinking about your work, tethered in confidence, not ego, tethered in rigor, not a facade, it's important to set the stage. And setting that stage requires you to do two things, right? And the first is what distinguishes a strong argument from a weak one? It's very fundamental, right? So I'm going to give you an example of a piece of literature that is in review right now in Nature Neuroscience. And for some of you publish, you understand that Nature is one of the largest and most important journal in science within respective fields. Prior to the institute that I'm in now at the University of Oregon, I was at the Howard Hughes Medical Institute at Geneva. This is one of the institutes where you have people like Eric Betsy, who invented light sheet microscopy and won the Nobel Prize for it. And in this institute, um, there was two competing ideas. The first idea is the university that I'm in right now, at the University of Oregon, where these researchers found this. They showed that when the animal is moving in the world, eye movements are important in understanding neural activity, right? What I'm going to do is I'm going to stop talking and I want you to appreciate these two different examples. Notice that in the one at the bottom, the eye is barely moving. In the one at the top, the eyes are moving. This one at the bottom here, just to give you the language required, it's called orofacial movements. You and I do it all the time, unconsciously. So what you see here is this animal making orofacial movements, kind of, wiping his nose, touching his nose. And you notice here in this animal here, it's moving its eye. The difference between this animal and this animal is that this animal is freely moving in the world. You can imagine, let's say you're going to, let's say Abuja or Lagos, right? You're moving, you're not fixed into the world. Whereas this animal is fixed. And the consequence of these two animals being fixed is that when you're not fixed, your eye moves more. When you are fixed, your eyes move less. And I think you don't have to be a physicist or a neuroscientist or anyone, anything with remarkable intelligence to understand and see these two different behaviors. Yeah. But I want to now show you what a bad argument is, right? My colleagues at Janelia published this paper recently, and you can see it says HHMI, Howard Hughes Medical Institute Janelia Research Campus. And they published this paper, and the title was Orofacial Movements, Not Eye Movements, Governs Neural Activity. And for us in the fields, this is actually an internal conversation people in these two fields that in neurophysics are speaking about in their own corridors of their labs. That we feel that this title did not was one of not only too arrogant but a bad argument because it didn't take into account these class of research. Because clearly you see that activity happens when the animal is making eye movements, not just someone seems yeah okay someone's annotating it for me, which is great. And so if you were to make such an argument in your own work, this would be something that I would qualify as a bad argument because you're not taking into account other experiments or other data points that could potentially challenge your own position. And as a thinker, someone that and as an analytical person, it's important not just to seek information that upholds your own belief, but also information that potentially challenges it. Because the point is not for you to be the person that gets it right or publish a paper. The point is to help the collective community move towards the truth or an approximation of the truth, right? So research, being an early career scientist, being a thinker, setting a stage isn't for you to articulate a position just because it's convenient for you, but because it is honest and it is rigorous in a way by which you are trying to lead the community towards a collective answer. And so if we were to now rewrite the title of this paper, what we actually should do is append the following: Orofacial movements, not eye movements, governs neural activity in head-fixed mice, which is these class of studies. But to make the general statement and assume that it's happening in non-head fixed and head fixed, that is what constitutes a very poor argument. And so what I've done here is just give a simple example of literature that I interact with frequently, where you have a bad paper that overgeneralizes and makes an argument that is insufficient, and what you could do if you were to rewrite this paper and make it a argument that someone finds respectable and believable. Yeah. Um, and so I'll continue. I hope that made a little bit of sense. And again, I apologize if these are some of this literature isn't familiar to some of you all, and I hope that you just get the general gist of what I'm trying to say, and I hope you can apply it to the domains of expertise that you're working on currently. I'm going to move to the third point. What makes a powerful introduction? So, for example, when I came onto this Zoom meeting, Professor Moranike, made an introduction, and she thought about that introduction before she made it. She found certain things that she wanted to highlight in order to compel you all maybe to come to the talk and so on. And so these are kind of general things that I think most people will do, which are very important. But what I want to do is I want to systematically kind of get down to some of the dark magic that makes a powerful introduction. Right now, I'm currently working on publishing a paper. And notice again, if any of you are making these connections, I want you to notice the game that I'm playing and how I sort of try to position myself at the center of gravity in my field. I want you to think of this title here. It's a pretty ambitious and some would say pretty radical title, right? A general theory of cortical time. If some of you are a little bit, aware of physics, for example, one of Einstein's most famous work is called General Theory of Relativity. And I will not be dishonest with you all. Whenever I'm thinking about my place in science, my place in the world, my place in society, I'm always trying to reference these giants in my own personal conversations. Because what I want to make sure to anyone, black, white, green, or yellow, who doesn't feel like Africans should be in these positions where we are at the center of gravity, I want them to understand that this is a return back to sender ideology. Let's just say. So when I think about my titles, my introduction, words that I'm using, it is very meticulous. In fact, I do it to agitate those who don't think that I belong in those spaces. And so this paper, I am trying to basically put forth a theory that explains the clock of all brains of biological systems, right? What is that clock that allows you to, speak to someone, remember what they're saying, you hold it in memory, then you continue that. What is the clock that allows you to put one leg in front of the other? What is the clock that allows you to breathe? What is the clock that allows you to wake up on Monday at this time and this time? What is the clock that allows you to throw a ball and catch it? That's what I mean by cortical time. How is the brain telling time? And this mathematics that I bring forth is to explain that phenomenon, such that whenever anybody in human history talks about the time and the clock of the brain, they have to mention an African, right? That is the audacity, and that is what Professor Morenica speaks about when we say dare to tell your story. I'm trying, every day I am trying to operate at the highest level of science, such that we are being represented, right? But let me move to that introduction that I told you about before this title. In the introduction, it's not important for you to kind of read what I have written here. Oh, sorry. But this introduction here, I'm going to read it to you all if you don't mind. It reads as follows. Cortex lacks an intrinsic clock, yet neural populations produce hierarchical activity across multiple timescales with striking precision. Right? So at first I state the problem that the field agrees with. And then I go on and say the circuit mechanism underlying this temporal organization remains unresolved. So that first two sentences, I'm saying something that everybody in the field, based upon my literature review, based upon understanding the problem, everyone agrees with. That these two things are something that the brain does, but the circuit or the thing that underlines this phenomena is unresolved. And then I state what I'm going to do. We theorize that the temporal hierarchy does not require generation. It's already encoded in the geometry of the connectivity. And so, even if you don't know anything about what I've just said, what I have done here is I stated the problem and the solution right away. No sugarcoating, no nothing. Just state the problem. What's your solution? Clean, simple, transparent. Right? Then after that, I go on and I talk about the different aspects of my solution, right? Which I've said. Time geometry alignment does XYZ. This is what it does, XYZ, right? So I state the problem and my solution. Then I go a little bit into the solution, why it is unique. In this case, the theory. Then after that, I talk about what new insights my solution provides, right? you can't really see this notation, and again, I apologize for that. But for those interested in this paper here, I basically solved a class of equations. Actually, actually no. Well, I will continue along this line. I don't want to complicate it with any mathematics, but I basically provide the equation, the calculation, the computation that the brain is performing when, we experience the process of time, let's just say. And so, um, in that, what new insight does the solution provide? And then after that, what you want to do is you want to speak to this point. Does the solution have any support? And for example, in this case of theory, is there any experimental support for it? And so these four components makes a very powerful introduction. And so let me just go back again, right? State the problem in your solution. Explain the different aspects of your solution. In this case, the theory that I'm working on, right? What new insights does your solution provide, right? Is it, as anything, whether it's physics, whether it's neuroscience, if it's not useful, no one will appreciate it, right? So make sure that the solution is useful, right? And then talk about how your solution is supported and the experiments or the insights or the future research that needs to be done, right? And so these three things, I would say, is foundational to the process of setting the stage and daring to set the stage in a way that you have the confidence and the audacity. But again, remember, rooted in the data, rooted in the rigor, and rooted in not looking for solutions or looking for evidence that supports your claim, but also that contradicts it, right? Because that's a sign of honesty, intellectual honesty, if I could say that. And so now I'm going to go into kind of the fourth component here that I've been asked to sort of shed some light into. Discussion, right? It is very, very um enticing for a thinker or for an academic or researcher to speculate. We speculate all the time, right? So, and some of our speculations are reasonable, right? What do I mean by that? If I threw a ball in the air, it's reasonable for me to speculate that that ball is going to come back down because of gravity. If someone opens the door for me, it's reasonable to speculate that this person has manners and it's being nice, right? If someone let's say, gives me a glass of water, right? It's not quite reasonable to think the person is going to poison me, right? Maybe it's especially in the context of, let's say, at a dinner, right? The waiter comes and, right? And so we speculate all the time, right? But some speculations are unreasonable and other speculations are reasonable. And so what I want to talk about in your discussion when you finally set the stage, write the introduction, you've done the work, is speak a little bit about the consequence of your work and speculate a little bit about what it could mean for the field. But remember, make sure your speculations are reasonable, right? And that's kind of what I want to kind of articulate, right? Let me give you a simple example before I go into the introduction, the examples for the introduction. The work that I've shown you, a little bit of my work with the general theory of cortical time, that work, if my theory is correct, it will fundamentally change not only how we understand the brain, but it will fundamentally be able to unlock the cure to things like Parkinson's, Alzheimer's, and so forth. Let me explain to you why that is. If you can tell, if you can explain why the brain, for example, how it generates sequences, like temporal sequences, time sequences, let's say time one, time two, time three, many of these diseases, when someone is, let's say, that has Alzheimer's, they can't tell whether or not the person that they're looking at is their daughter or just some random person because the ordering of their mind has been shuffled. So their inability, their clock has been completely compromised. Someone with Parkinson's, for example, Muhammad Ali was someone with Parkinson's. When he grabs a cup, for example, the neurons in his brain that normally orders this first movement, second movement, and third movement, they're now shuffling. They're now no longer stable. So if we can understand the clock that creates those ordered sequences, you can now reverse that clock. You can tune that clock. And that's the consequence of my work when it comes to the general theory of cortical time. And so that's an example. Now remember, I didn't say this thing will cure Parkinson's or Alzheimer's. I didn't say that. I said if the theory is correct and experimentalists measure the theory and my theory is good enough in specifying, hey, look at this part of the brain or look at these dynamics, such can be the consequence. And so that's just a simple example of exploring the consequence, but making sure you speculate in a responsible manner. And so let me give you simple examples of that, and maybe that'll hit home a little bit more. So in the paper, right? This is the first paragraph of the discussion, and I'll read it to you. Remember that in the introduction we talked about the circuit mechanism being unknown. So remember circuit mechanism, right? Notice that if you go back, remember that I had put here um, the circuit mechanism, right? Underlining its temporal organization remain unresolved. In the discussion, look what I said, how I framed it. We identify a circuit mechanism for intrinsic temporal hierarchy in recurrent cortex that unifies internally generated and sensory driven dynamics within a single geometric framework, right? So restating that problem, but now presenting the solution, right? And then I go into kind of the more detailed across analytical derivatization. And basically what this means is I didn't show you all the mathematics, but I'm referring here to the equation the solution. In mathematics, we have this thing called first order differential equations. And so I used first order differential equations to explore and investigate the rules, the mathematical logic that the brain could be using to create these ordered temporal sequences, right? And so what this means in short form is when you want to make a discussion, you say, hey, here's what I have done. You restate it and you be very, confident in it. Here's what I've done, right? Systematically and precisely, right? And then you say, what is the future implications for the field, right? And you state that, right? And of course, right, much of your work has to be cited. Here I just used the notation of 44, but if you go back into the paper, you'll see that 44 refers to a particular study, right? And so again, you articulate what you have done very precisely, very confidently, and then you talk about the implications to the field that your work could potentially have. And again, remember, speculation is great, but speculating responsibly, having that level of control, right? Because Again, these things are important when you are undergoing a particular class of research, whatever field. So I hope that was clear. Now I'm going to move into the latter part of the talk, right? This part, I want you to, I want, again, I know that there's a lot of mental gymnastics and flexibility that I'm asking you all to undergo because, I'm sure that, people have different diverse fields. Yeah. And so again, as I continue, just try to take whatever you can and apply it in your own unique way as you tell your own story. So I want us together to get into a very simple experiment and try to tie all this together and bring this all together. As you know by now, right? What I do is, as a physicist, I work with neuroscientists and biologists. They have all of these phenomenons they're trying to explain. Some of them are trying to explain how neural activity affects movement, how people in Parkinson's are remembering to forget. And you might say, well, why don't they just do experiments? But some of those experiments, they're very, very hard to interpret. So they bring in people like myself with physics and math, and they say, hey, help us use your tools to get a different idea of the unseen. So a lot of what I do is I try to, I'm always trying to use math and physics to kind of pull out things that it's hard for the eye to really understand and see. And that's really what the heart of physics is. And so what I'm going to show you is a simple experiment done by these individuals, my colleagues here at the University of Oregon and at Geneva and at Harvard. They put a mice, right? Because remember, they're trying to solve the brain. They can't do this to a human being. That'll be cruel and unethical, right? Not saying that this is not unethical, but that's a discussion for another day, right? And so they want to know, what is the mice doing? Right? Because if we can understand this, then maybe we can abstract that and use it to understand what humans are doing, right? And so what I'm going to show you is an experiment. But remember, I told you that those experiments, they're not always clear what it means, what to read from it. It's almost like dark magic in a sense. This animal, right? It actually doesn't see this green thing that you and I see. This is just to visualize it. Its goal is so it has this kind of thing here is a reward port where it gets water, right? Because that's the motivation of doing the task. So whenever it hits the right place in space, it'll get water, right? So so it's now getting water. Now one of the other spaces activate. Again, it doesn't see it. Now it gets water again, right? Now, all of those things it makes sense to you and I's eyes, right? Okay, it finds it and then it gets water. But look at this trial here. You and I can see this, but you might wonder to yourself, like, why doesn't it just go there and get water? Right? There's something else happening that you and I can't see with the naked eye in this animal's brain that it's causing it to miss this thing that you and I can see. Right? And so this is where mathematics comes in. And I don't want to get too deep into kind of how I tell the stories and how I abstract and how my brain works. But for any of you who understands certain parts of physics, one of the key things that physics tries to understand, it finally got it. Let's go back a little bit. One of the key things that physics tries to understand is what we call stochasticity. Sorry, just keep going back here. No, going too forward. Um, just I just want to play it again. Sorry about that. Um, yeah. And so while I speak, I'll just one of the things that physicists try to understand is what we call stochasticity. Or what that really means is like spontaneous behavior. Things that look random, do they have order? You get me? So you can abstract that way of thinking to this problem because this animal is just moving around, and so there's times where you see a little bit of chaos, right? That the case where you and I see it, but it's like moving around it, right? Something funny is happening. And so what we want to do is we want to use some of the intuitions in physics to kind of explain what could possibly be going on, right? And so we have a problem. This problem is randomness, right? We see the dot, the animal doesn't see what is happening. So one of the things you can do, yeah, is one of the ways that I've solved this problem, right? Or looking to solve this problem. And this is going to go a little bit into AI, so I apologize.
Okay. We're going to have to finish shortly in another 6 minutes.
Another 6 minutes. Okay, excellent. One of the things that we do is you can create an AI agent to simulate that mice's movement, right? And what I'm and the implications of this work is actually being used by companies like Elon Musk for their humanoid robots, right? Because that is kind of what the Western world is moving towards right now. How do you replace human beings? I don't want to get into the ethical parts of what they call transhumanism, right? Because again, the psychology that they have and the is very different from our worldview. Let's just say, right? But the point that I want to make is that one of the tools that you can use is artificial agents to try to simulate this mice in order to see if you can pull out some of the rules that it may be using. So you then compare the agent and the real mice. And to create such a thing, you need mathematics and physics. But what I'm going to do is I'm just going to give you all the answer and give you an example of how you can do that. And again, this thing that you're seeing here, some of you are some of the first people in the world to actually see these sort of this sort of data that I'm presenting to you. What you're going to see is you're not going to see the actual agent. You're going to see the path that the agent is traveling. So what I've done is this agent is going to move into this world autonomously. No one is controlling it. It's going to move into in this world. This is an artificial world, and you can and I think as you see this, you can appreciate how this is relevant to something like robotics and artificial intelligence and companies like the humanoid robots that Elon Musk is creating. We are kind of trying to create the brain of these robots, right? And so some of these technology and this storytelling is by questions that neuroscientists bring to us and say, hey, we don't understand how the animal is moving. We say, okay, well, let's create an agent to replicate movement and see whether or not we can learn from some of the statistics and then apply it to the problems that you all are facing. And as you can see, this agent is moving into the world as if it was a actual real human being, right? Fairly well, right? It's not jumping into the water, right? It's not bumping into things. Sometimes you can see it's struggling a little bit, right? Because it looks a little bit drunk, right? Sometimes, right? But for the most part, right? This time it moves a little fast, right? It's looking up in the sky, right? You know, I sitting in the position that I sit, and I thank God for it, right? Like, I don't, I don't really always look back as much as I should to appreciate kind of the things that I get to think about and do all the time. And but a lot of these things are the cutting edge of science and innovation. And I'm saying that to say that wherever you are in your own journey, my prayer is that each and every one of you um not only one day or even in the spaces that you are, continue to chase your dreams and your research, but hopefully even become, greater than I, right? And move whatever fields you have forward. Because I think that constitutes to moving Africa forward in very profound ways. I'm just gonna show you kind of what this model was able to do eventually. So On the left-hand side is the mice. I just took like a snippet of its movement. And notice that the actual model is actually starting to predict the movement of the mice. It's not perfect, but you can see it's starting to predict it in very precise ways. And so these are some of the ways in which you can get at solving problems. I'm going to close this out with a very, very provocative point. I want you to I talk to Professor Morenke about this quite often. One of the reasons why one of the heads that I wear um, is a scientist because when I see pictures like this, I see I don't see myself here. I don't see you. I feel completely erased from the discussion. You know, one of my mentors will tell me, if you're not at the table, you're on the menu. What I find very violent about this picture is that our representation is completely missing. And so the question I want you to ask yourself is, where are you here? Where are you when you see this thing? A lot of these people I admire. Don't get it wrong. This is Nikola Tesla, for example. This is Einstein. This is Marie Curie, Dirac, Niels Bohr, Charles Darwin, right? Max Planck, right? But I am very sure, without a shadow of a doubt, that there are kids in Africa that if you gave them 10% of what these men or these women got, they will completely run laps around these people. I am 1000% sure. I've went to the best institutions in the world. There's a lot of great minds in Africa. And my prayer is that this talk motivates you to understand that you can also be at the table. And so I leave you with this. We have systematically been erased in the discourse of science, in the discourse of creation, in the discourse of innovation. That has to change, right? You are needed more than ever, right? Forget about the money, forget about the external validation, forget about APC, ADA, whatever, forget about all that. We need to ground ourselves in the science, in the critical thinking, in the innovation, because we are the future of Africa. The 100 people in this room, we constitute the future of Africa. And it starts with storytelling, rigor, so forth. And so I want to tell you this. Your story and your research can introduce a new kind of human history, right? Someone in this room can find the cure to Alzheimer's, can create the next design principle for medical health in the world, can figure out, for example, the cure to cancer, right? A new kind of human history led by the African mind. Of course, we're not saying that we as Africans, we create things and create an apartheid way of science. No, no, no. We just want to be at the source of innovation and creativity while the world also benefits from it, right? And so I want to encourage you further that your work and your research can create a new kind of human history. And again, I'm very grateful for this opportunity. I'm humbled incredibly. I'm always very, very happy when I get to speak to my own people. I feel less alone. It feels less isolating. I feel less weird, right? I always tell my mom, hey, I'm a theoretical physicist, and she's like, what is that? Right? Partly because, that is not something that we find useful, but I know that you all are a little bit more closer to that mentality. And like I said, you are needed more than ever. And thank you for listening. And I hope it wasn't too complicated or complex. And I hope that you're able to take a little bit from what I've shared. And the last thing is, if you want to connect with me, please ask for my email from Professor Morenica. I'm more than happy to have personal discussions. You can also connect with me on this website here. This is one of my companies. And what we are doing is we're pioneering this concept of digital twins, where you're able to interact with my twin who has the same cognition as me, who can engage with you. You can get knowledge from it. You can ask it questions. You can talk to it. I know it's a crazy idea, so you have to excuse me, but again, I'm interested in rewriting a new kind of human history, and this is just an example of one of the many things I do to try to move the field forward. And so what you see is my twin kind of talking to the person that's asking it questions about, how do you publish in science and so forth. Again, I hope this was very helpful, and thank you again for the opportunity to share my story with you.
Thank you so much, Ife Daya. I'm almost in tears. You can see why I brought him here. Guys, there to tell your story. You have a story to tell. We have stories to tell. And you are in that space to tell the story. You just have to dare to tell it. You have to know you are important. This is not about writing papers for numbers. This is about telling the African story. No other person can tell but you. Dare to be significant. Dare to be a Newton. Dare to be an Albert Einstein. Dare to be. And set that stage to own the space by being rigorous in your claims. As you're writing, anybody would have thought if I was there at this morning session when we were talking about introduction, the exact four things Kudus was talking about. Exactly. And anybody would have been there earlier at 3 o'clock, thinking if Dyer was there, when he was telling how you can tell stories, you can do commentaries, you can do editorials, but ensure that it's a powerful introduction and you are responsibly discussing. Guys, there's nothing else we can do but let you know that you have an example of somebody who is there to tell a story and is walking lonely in the space, but he has chosen to be in that space because of you and I. We as Africans have a story to tell. On that note, I want to say thank you, everybody. Thank you, Fedai. I'll be with you shortly after. I still have an hour session with those on OHI. And at this time, I say thank you, everyone. Please exit. And for those on the OHI team, please stay on as we go to our third and final session. God bless you all. Have a wonderful week. Bye. Kadis, you're going to work with me to quickly move people out so that those on OHI would stay. The only way I can know you're on OHI, your group asks you to give instructions by hyphening your groups. So the only people would allow to stay will be those that hyphen the group, profile, so on and so forth. Any other person that did not hyphen the group will be treated as a stranger at this time. Thank you once again. Let's take a 4 minutes break, and then we'll go on to our next section on oral, the OHI group, and Fola, you'll be taking the group. Thank you. I'll be working with Kudus to exit those that do not have hyphens. There's no way we can identify anybody that's on the group without the hyphen. So give me 4 minutes as we walk through
Okay,
this.
thank you.
Thank
Thank
you.
you.
Yeah.
Hi there, please, you can stop live streaming.
All right, sir.
Thank you.